Hello and welcome to another video on tolerance stackup analysis. In this video, I'll be taking you through on how to do a tolerance stackup analysis for angles. What is the maximum and minimum possible angle for a specific angular specification in the assembly. So let's say if you're having two parts which are being assembled. So this is one part and this is another part, the sand color part, and then it is being assembled using fasteners. So the main block has two threaded holes. This is one threaded hole, this is another threaded hole, and this sand color block has two clearance holes. So basically we want to find out the specification over here, that is the angle made by this slanted surface on the sand color block with this flat surface, straight surface on the base block. What is this angular specification? What is the maximum and minimum possible angle after assembly? We want to find this out. For simplicity's sake, let's keep it limited to coordinate tolerancing, dimensioning and tolerancing, which is this shown over here. The two parts are dimensioned and toleranced using the traditional way, that is coordinate tolerancing. And you can see that the location of the holes have been specified with respect to certain references. So you can see this sand color block. So the location of the two holes is specified using these three dimensions, 1, 2, 3, and the size of the hole, the basic size of the hole is 7 and the size tolerance is plus or minus 0.1, and this is the angular specification of this slanted edge. For the base block, these are the two holes. These are M6 tapped holes, and the position of these holes is toleranced as shown. So these are the two drawings. Based on these two drawings, we will calculate what is the specification of this angle in the assembly, what is the angular specification, what is the maximum angle, what is the minimum angle. We want to calculate this, and we will do this by understanding various sources of deviation. So what are the various sources of deviation? The first deviation source is the deviation in the location of the two holes on the base block, which is the tapped holes. The deviation in location of the two holes based on these specification, that is the deviation in position of the tapped holes. Second source of deviation is deviation in position of the clearance holes. So because of the deviation in position of the tapped holes, the inclination of this top edge will increase or decrease. Similarly, because of the deviation in position of the clearance holes, the final inclination in the assembly of this edge will increase or decrease, and also the deviation in the angle of the part, which is nothing but this specification, which is because of the part manufacturing. And finally the deviation due to assembly shift. So when we are assembling a part using clearance holes, as you can see, there is clearance between the bolt shank and the clearance hole. So that clearance will cause assembly shift. So considering worst case assembly shift, what is the worst case deviation which we can have in the angle? That's what we will find out. So the first source of deviation which is causing the angular impact is the deviation in position of the tapped holes. So the tapped holes are positioned using the coordinate dimensioning and tolerancing scheme. So that means that when we say plus or minus 0.1 over here, and over here, we mean that the tolerance zone is a square of 0.2 side. That is, because of these tolerances, the tolerance zone shape is a square having a side of 0.2. The length of the side of the square is 0.2 on either side, and basically the center of the holes should lie within this square tolerance zone. So that is what is meant by this drawing, that the center of the hole should lie within a square tolerance zone of 0.1 into 2, that is 0.2 by 0.2 on either side. So now to calculate the angle, we need to calculate it using geometry. So this is a magnified view of the two tolerance zone, an exaggerated view of the tolerance zones. So these are the two true position centers of the two holes, and if we are considering that the center of the two holes can vary within these tolerance zones of square shape, if one center of the hole, that is this hole on the left hand side, is over here and the right hand side hole is over here, that means that we will get the maximum angular deviation. To calculate that maximum angular deviation, which is this angle shown over here, we can use the geometry and calculate from the data. So this right angle triangle is what we are trying to calculate for the angle. So for that we need the height, this vertical height, which is nothing but half of the side of the square, which is 0.1, and the distance between from this point to this point. So that distance is 40 minus 0.2 divided by 2. So from this point to this point is 40, because 50 minus 10. So the basic dimension is 50 over here and basic dimension is 10 over here. That is the true dimension. Is 50 minus 10 is 40. So from this point to this point is 40. And we are cutting off this portion and this portion, which is 40 minus 0.2. That is 39.8 divided by 2 is 19.9. So from this point to this point is 19.9 and this side is 0.1. So we calculate theta as 0.29. So the variation will be plus or minus 0.29, because it can go positive, it can go negative. The second source of deviation is the deviation in position of the clearance holes on the sand color part, which has the angled profile as shown over here. So these are the specifications and the procedure is very similar. So the tolerance zone shape is the same. These are the dimensions which are positioning the hole, and the tolerance zone shape is the square shape. And we are calculating the same way, because the center to center distance, the true distance is the same. 48 minus 8 is 40. And then this distance from this point to this point is again 39.8 divided by 2 is 19.9. 19.9 and 0.1. Adjacent is 19.9 of the angle, opposite is 0.1. So opposite by adjacent, we will get tan theta, and tan inverse of that we will get theta. So theta is equal to 0.29 degrees and variation is plus or minus 0.29. Now the deviation because of the position of the tapped holes and the deviation in because of the position of the clearance holes does not always stack up. This does not always stack up, because as the position of the holes on the base block, it changes, the orientation of the part will eventually match the position of the holes on the base block. So we orient the part as per the position of the holes on the base block when we are assembling. Hence the deviation in position of the clearance hole does not actually stack up. It actually goes into assembly shift. So this is just to get a feel of what kind of deviations will occur. The next source of deviation, which is the third source of deviation, is the deviation in the angle of the part itself because of the part manufacturing, the angle, change in angle of the profile of the edge, which is this one in this angle shown, which is 10 degrees plus or minus 0.2. So of course it can be manufactured at perfectly 10 degrees. It will have variation because of the manufacturing process. So that is the plus or minus 0.2 degrees, and that we can take directly as the source of deviation, the third source of deviation, plus or minus 0.2 degrees. So to recap, there are three sources of deviation. The first source of deviation is the deviation in position of the two holes on the base block, which is shown over here in the red color holes. So it can move up, it can move down. Second source of deviation is deviation in the clearance holes position. It can move up, it can move down. And the third source is the deviation in the profile of the part itself. So the angle is steep, angle is small. The fourth source of deviation is the most impactful source of deviation, which is the assembly shift, which is nothing but the shift of the part when the part is being assembled onto the base plate using the fasteners. How much shift will take place because of the clearance between the bolt and the clearance hole. It is nothing but the shift which is happening when assembly takes place. What is the worst possible shift which can happen? That is what we calculate. So let's just simulate this. So we have the base block which is having a tapped holes. So the tapped holes are manufactured as per their own tolerances. They can have deviation in their position. Now when the block, the angle block, which is this one showed over here in this drawing, is brought to assemble on top of the base plate, the block will be angled, it will be rotated to match the clearance holes on the block, will be rotated to match the tapped holes on the base plate. Now when it is rotated and when you fasten it, there will be a clearance between the fastener and the clearance hole on the on this block. So when we are fastening the bolts, that time shift can happen. It can move around. The part can move around until it is perfectly tightened. We cannot ensure that it will be perfectly centered as per the clearance holes. Of course, that is a degree of skill. If the level of skill is higher, if it is automated assembly, then this assembly shift may not be considered. But if we are considering the worst case, that the operator assembly along with is assembling the part along with the assembly shift, then this has to be considered. So what is the worst case assembly shift? It is nothing but a function of the clearance, the maximum clearance which can be there, which is the clearance between the bolt and the largest clearance hole. So the largest clearance hole is 7.1. that is the basic dimension of the clearance hole is 7, and it is having a tolerance of plus or minus 0.1. So the maximum size of the hole can be 7.1. So this is the cross sectional view of the assembly. This is the base plate, this is the fastener, this is the sand color block, which is angled block, and 7.1 is the maximum size, clearance hole size, and the M6 bolt is, we are considering that it is 6 mm. So 7.1 minus 6 is 1.1, 1.1 divided by 2 is 0.55. So 0.55 is the shift which can happen. So using this, we can calculate again using the trigonometry. 19.9 is the center to center distance, and we are calculating using 0.55, we will get delta theta 4, which is plus or minus 1.58 degrees. You can see that this value is much higher as compared to the earlier ones. And the next step is to calculate the stack up. So the angle stack up is calculated by adding all of these tolerances of the angles. The first deviation is plus or minus 0.29 degrees because of the angular deviation of the two holes on the base plate. The second is cancelled out by the first because we are considering it is self-centering assembly. Delta theta 3 is deviation in the angle of the part itself inside the part, plus or minus 0.2, that is from the drawing directly, and delta theta 4 is assembly shift, plus or minus 1.58 as we had calculated. So calculating the total, we get plus or minus 2.07. So this is the maximum shift deviation which is possible, which is 10 degrees plus or minus 2.07. Maximum angle is this, maximum minimum angle is this value. So this is a very simple angle stack up for a part which is assembled using two holes. Of course, if there are more number of holes, it becomes more complicated and we need to have more advanced calculations for calculating that. But this is a good way of calculating the worst case angle which can occur due to assembly shift and the other variations combined.